Hello, I'm Mike McCulloch. Today I'd like to give you a much more elegant cosmology than the standard one. As you know, the standard cosmology and observations from 1999 by Rees and Perlmutter proposed that the universe is not only expanding, moving away from itself, but with these recent observations it also appears to be accelerating away from itself, and the amount of energy required to do that is incredibly large because the universe is very massive, about 10 to the 53 kilograms, 10 to the power 53 kilograms. So the amount of energy required to persuade something like that to accelerate away from itself is mind-boggling. So I'm going to try and show you today how quantized inertia proposes that the cosmology we need is far simpler. It's steady state. There's no need for all this accelerational energy. So we could start off with these formulas. So we can do it in 4 lines. So here's Newton's second law at the top left, F equals ma. And we can also say that we have, let's say we have an object, a smaller object moving away from a larger one, which is large m, smaller object means small m, and it's gravitationally pulled back. So the force is negative gmm over r squared, where r is the distance between the two objects. But with quantized inertia, there is a slight difference in that the inertial mass, so the little m of the ma, has a little modifying factor that it must be multiplied by. So we get line 2, and you can see the multiplying factor here is in the brackets. It's 1 minus 2c squared over the acceleration of the object times the cosmic diameter theta, and the rest of it is the same. Now if we simplify this a little bit, we get line 3. So you can see that I've multiplied through by a, and that gets rid of the a on the bottom of the second term, and it adds an a into the first term. And then we can take the second term in brackets onto the right hand side, so it becomes positive. So we get the acceleration of this object, so moving away from the smaller one, moving away from the larger one, is given by minus gm over r squared plus 2c squared over theta. So this tells you immediately that whatever acceleration, gravitational, electromagnetic, or whatever we have in the first term, whatever acceleration we have there is a second term which is independent of the mass and is very small, because c squared over theta is about 10 to the minus 10, but it's there, and in this case it's going to oppose the gravitational contraction. So you might think that, yes, okay, so quantized inertia predicts an extra acceleration, and sure enough, if you take the acceleration of the edge of the observable universe, this actually predicts it. So this predicts the cosmic acceleration, which has been attributed to dark energy. But it's not just that. If you think about the wider picture, and here I'm referring to a book, I read a book by Alexander Unziger, The Mathematical Reality, and somewhere in there he says something like, what happened was that astronomers saw the universe expanding, and they expected it to be decelerating because it was being pulled back by the mass of itself, its own mass, gravitationally. But they didn't observe that pullback at all. So that is why they had to postulate an acceleration, the cosmic acceleration, in 1999. But it would be far easier to just assume that there is a steady state, as it was always said by Fred Hoyle many decades ago, and that you don't need any extra energy to cause it to expand or accelerate. And interestingly, quantized inertia gives us a way to produce this balance, because if you look at this equation, we can say that the second term here is opposing the first one. So the gravity is pulling the object back, whereas quantized inertia, the second term, is pushing it the other way. This could be the origin of the balance. So is it the origin of the balance? Well, if it was, then we could equate these two terms on the right hand side and work out to see whether they are equivalent, and whether A actually becomes zero. And when we put in values, so we know the value of the gravitational constant, we know the mass of the universe, big M, we know its size, r, we know the speed of light, and we know its diameter, which is theta. And when you put these values in, you found that these two terms predicted by quantized inertia match. And so this is very good evidence that this cosmology does actually make sense and reflects reality. So yes, that saves an awful lot of energy, probably the largest energy saving in human history. Okay, so I hope you've enjoyed this short, and I'll see you next time. Goodbye.